Okay, so now we will do a little bit of mathematical modeling. Okay, so calculus is required for this one. For this course, it's a prerequisite. As you could see, despite the fact that the calculus is prerequisite, a lot of the sort of calculus that we've been using so far is vector calculus. Okay. Integrals and this and that would be used in derivations normally. I didn't have a lot of time for that. I've done a lot of mathematical modeling for you guys, and then the conceptual understanding. And calculus has its place. Okay, so I'm just going to show you a little bit of calculus here. I'm not going to put too much emphasis on this because you will get to take the same course again at a higher level. When you guys take it at a higher level, you will take it in mechanics. Mechanics is going to come in two flavors. You will take engineering statics, and you will do these problems in engineering statics. It's going to be chapter number 9 because I've been teaching engineering statics all along. So everything that we've done in terms of physics, they're not going to put the emphasis on the understanding of physics. At that point, the emphasis is on the mathematical representation of these concepts. Okay, guys, this is the only place where you get to master physics. So it's a pick and choose moment for me. No one is going to teach you physics from now on. All right. If you don't understand physics, you will struggle for the rest of your lives when you're doing engineering. Right. I did the best so far, so you have a really good understanding of physics. Mostly stuck to algebra so far because you can get to physics easier from algebra. More mathematical it gets, the thicker the math gets, the less you're going to be able to get to physics. Okay, now that we have done quite a bit of physics, let me illustrate the same concept a little bit more sophisticatedly, using a little bit more sophisticated math. Okay, guys, this is your blob. Okay, welcome to real life. Solid mass that you have. It doesn't look like a sphere. It doesn't look like cylinder. This is what you get. You get this blob of mass, and then you can just rotate it with respect to a point. This is known as the axis of rotation. All right, so this is the radial distance to one of those points that you're looking at. So it's going to be 90 degrees to the axis of rotation. So this thing that you're looking at, this is the mass. So what you need to do is you have to grab a small segment of that mass. All right, so delta m becomes dm, delta m, so which means that you're grabbing a small portion of the mass. And then you take this mass, and this mass times the square of the radial distance to the point of rotation with respect to the rotational axis, if you want to be exact, is going to give you a moment of inertia. Now what you need to do is you need to take this mass and then grab this mass and grab that mass and then keep calculating the moment of inertia for every and one of them and just keep summing them up. The summation of all the moments of inertia of each and every single segment is known as your integral sign. The summation sign becomes the integral sign. And so as a result, you just sum up the total mass of this tiny little chunks of mass distribution. And it's going to give you the moment of inertia with respect to this rotational axis. And then another thing that you do, and this is one of the future topics that we'll cover, you express mass in terms of the density. All right, density is the amount of mass per volume. All right, so the density is going to be expressed in terms of the density and density times the differential of that volume that you're looking at. All right, so this turns into a volume integral. You're looking at density assumed constant. It doesn't need to be constant. All right, so this is your volume integral. That's what we say. The volume integrals, I don't know if Calc 2 or Calc 3. I think these are Calc 3. All right, so means that these are going to be three-dimensional integrals that we end up getting. Okay, so this is a generic statement of how you figure out the moment of inertia for any shape that you're interested in. All right, so that's a generic statement. So which means that now that we made a generic statement, I just want to show you how to do at least one of them. At the same time, I want you to see that these concepts will be re-expressed in a little bit more mathematically sophisticated manner. At this 8:25, go take a short little break, and then we'll take it from here. Okay, moment of inertia of a cylinder is going to be 1/2 mr squared. All right, so how do we come up with those kind of things? Here's how. It's all calculus. All right, so the height, 1/2 is going to be here, the other half is going to be there. So it's going to give you h along that direction. R is the radius. All right, so the moment of inertia is going to be expressed in terms of the rotational axis. Rotational axis is going to be z in this case. So it's going to be rotating with respect to z. Definition, moment of inertia is going to be this mass and the square of the distance to the rotational axis. Okay, so it's an individual mass. So you're looking at all these mass segments and then you just sum them up. We did formula just before that. So what I'm doing is I'm going to use the same formula. All right, so the distribution of mass is going to be expressed in terms of the uniform density being distributed over the volume that you're looking at. So this will become a volume integral. All right, so the entire volume of this is the pi r squared, which is this, times h is going to give you the volume. If you wanted to express the volume in terms of a volume differential, what you need to do is you have to differentiate the left and the right-hand side, so the volume could be differentiated along the radial direction. So you end up getting this expression. All right, if you have no idea what I'm saying, it's perfectly fine. I'm using expressions from Calc 2. All right, so the volume can be expressed in terms of differential volume element. So when you differentiate this, the right-hand side is going to differentiate with along the radial direction. So you do a back substitution. And all of a sudden you realize that your variable becomes r, so you can integrate everything with respect to r. So you got r here, you got r here, and then you got the differential of r. All right, so the constants, you can just take them out. So h is not going to change, 2 pi is not going to change, so you have to put in front of the integral sign. All right, so r times r is going to be r cubed, squared times r is going to be r cubed. So and you have the differential of r dr. All right, and then we will integrate this between 0 and capital R. This becomes the radius of it along the radial direction. So when you take the integral of this is going to be r to the 4th divided by 4. So do a back substitution. So this entire expression is going to become that. Oh, this is neat. All right, so then simplified. Obviously, 2 is going to go into 4 2 times. And so this is going to give us 1/2. Okay, what else do we have? Okay, now we have to simplify this expression. So which means that the density needs to be expressed in terms of the total mass. So we got to express the density in terms of the total mass. All right, so you have to just add up all the masses of this volume. Right, so m is going to express all the masses of the volume. So the differential mass can be expressed in terms of the mass density times the differential volume. And the volume of a cylinder is this term. Differential volume of the cylinder is going to be that term. So I just drop it right here and put it back in there. And then 2 pi and h, those are constants. So I just put them in front of the integral sign. And what do we have? Now we have to have it integrate r along the radial direction. So this is going to give us r squared divided by 2. Back substitution. All right, so this is going to give us the total mass. All right, so we came up with the expression for the total mass in terms of the density. All right, so density needs to be expressed in terms of the total mass. Now that we got an expression for density, we'll take density and just plug it in there. And then we'll simplify everything. All right, so h, let's cancel, pi is going to cancel. And don't forget r squared. R squared to the 4th, so you get a cancellation. All right, so we end up in 1/2 mr squared. This happens to the moment of inertia of a solid cylinder. Okay, guys, this is how it is done. I think this is chapter number 10 in statics. All right, so we'll be spending a lot of time doing these computations in the future.